Before we begin our discussion of spray equipment technologies, operator techniques, and equipment setup, it's important that you understand the terms that we will be using in this program. Atomization is a process whereby a liquid coating is converted into fine spray particles or droplets so that the coating can be applied to the surface of the wood in a highly controlled and even manner. Excellent atomization is achieved when we have the right mixture of fine and medium-sized particles with very few coarse particles. Good atomization, on the other hand, is comprised of a mixture of mostly medium-sized particles with some fine particles and some coarse particles. Poor atomization occurs when we have the majority of our particles being large with few medium-sized particles and almost no fine particles. To achieve atomization, some guns use compressed air, which is controlled by an air regulator and is often referred to as the atomizing air. Other technologies, such as air-assisted airless, use a combination of fluid pressure and air pressure to achieve atomization. Airless technology just uses fluid pressure. Fluid pressure is an integral part of your atomization process. The fluid pressure is controlled by the amount of air pressure that is applied to your pressure pot or pump. In low-pressure technologies such as air spray and HVLP, the fluid pressure is used to convey the coating to and out of the gun. In higher pressure technologies such as air-assisted airless and airless, the fluid pressure is the main source of atomization. In either case, the fluid pressure determines your flow rate. The flow rate is the amount of material exiting the gun in either ounces or cc's per minute. The flow rate determines how fast the operator will be able to spray. Controlling and knowing your flow rate is a critical part of the atomization process. The term overspray refers to the fog or paint particles that exit the gun but that do not actually end up on the part. Instead, these particles float in the air, sometimes landing on a freshly coated surface or on the floor of the booth or the walls of the booth or into the spray booth filters. The amount of overspray is directly related to the spray gun technology being used and the pressures that are used to operate it. The amount of overspray is directly related to the gun's transfer efficiency. Simply put, transfer efficiency is the percentage of solids leaving the gun that actually end up on the part. In general, an air spray or conventional gun is only about 30% efficient. This means out of a gallon of coating, only about 1/3 of a gallon actually ends up on the part being sprayed. The other 2/3 of a gallon end up on the walls, the floor, or in the spray booth filters. Other types of spray guns, such as HVLP, can be up to 65% efficient. This means that 2/3 of that same gallon will now end up on the part instead of the floor, the walls, or in the filters of the booth. In this case, you would end up using 50% less material, which would equate to a 50% reduction in VOC emissions. Airless guns are only 40 to 50% efficient. This means that less than half of the material sprayed actually ends up on the part. Some air-assisted airless guns could be up to 80% efficient. This technology can enable manufacturers to use 50 to 75% less coating to cover the same amount of surface area compared to a conventional siphon feed gun. To understand why some guns are more efficient than others, you need to understand spray particle velocity. To understand spray particle velocity, we need to pretend that this tennis ball is a particle of paint. During atomization, The paint particles are accelerated forward towards the object that we are spraying. Those particles in turn bounce back and are what we call overspray. These particles can travel at different rates of speed depending upon the atomization technology used and the amount of pressures used. By virtue of their design, each atomization technology delivers a different particle spray velocity, which directly affects each gun's transfer efficiency. Guns that have the lower particle velocity will tend to have the higher transfer efficiency. This graph illustrates how spray particle velocity affects transfer efficiency.